My name is Doug Carlin. I am a research soil scientist with the USDA Agricultural Research Service, ARS, located at the National Laboratory for Agriculture and the Environment in Ames, Iowa. Recently, I've had the privilege to serve as chair for CAST issue paper number 48, entitled Energy Issues Affecting Corn-Soybean Systems, Challenges for Sustainable Production. During the next few minutes, I would like to share some of the background, perspectives, and conclusions presented in this report. I would like to begin by acknowledging my co-authors, Drs. Dave Archer, Adam Liska, and Seth Meyer. I also want to thank the CAST reviewers and everyone else who contributed to this project. Energy issues, even for a relatively simple corn-soybean system, have been and continue to be influenced by many factors. First of all, corn and soybean production practices as they evolved during the latter portion of the 20th century were generally based on cheap and abundant energy supplies. However, due to increasing global demand, more variable weather patterns, and greater uncertainty regarding future energy supplies, it has become more and more important to critically evaluate all aspects of energy production and use by our agricultural systems. For this issue paper, my co-authors and I have chosen to frame our evaluation of corn-soybean energy issues based on the concept of sustainability. For consistency with other evaluations, our assumptions were that energy, conservation, and efficiency are the most important considerations, and that corn-soybean systems must continue to have a positive local and regional economic impact. We therefore define sustainability using the Farm Bill definition, which states that to be sustainable, systems must satisfy human food and fiber needs, enhance environmental quality, make efficient use of non-renewable and on-farm resources, and enhance the quality of life for farmers and society. Simply stated, sustainable systems must be economically viable, environmentally benign, and socially acceptable. To understand why it is difficult to quantify energy issues associated with corn-soybean systems, it is important to recognize that this seemingly simple crop rotation and its energy and use involves genetic resources, nutrient supply chains, many different types of equipment for tillage, planting, and harvest, and a wide array of potential pesticides for optimum crop care. Furthermore, our model system is also dynamic, as evidenced by the 500% increase in the land area to which soybean was planted between 1950 and 2010. In other words, the corn-soybean system that evolved based on cheap and abundant energy supplies ensured a consistent commodity supply and resulted in numerous products from which we all benefit. But it also raised many conservation concerns and increased our dependence on fossil fuels. Digging deeper into the energy issues affecting corn-soybean systems, an important first step is to clearly define the system boundaries for which the assessment is being made. For example, are tillage, seedbed preparation, weed control, fertilizer use, manufacture, and transport to be included in the analysis? For what time period our evaluations are being made? What heating values are being used for the various energy sources? What assumptions are being made regarding greenhouse gases? Are the scales for each subsystem consistent and appropriate? Indeed, the boundaries associated with corn-soybean systems can be complex, but even relatively simple analyses show that energy accounts for almost half of the total operating cost for corn production and 22% of that for soybean. The bottom line for this and many other crop production systems is that decreasing tillage intensity is very important for energy conservation. Nitrogen management also has a strong effect on energy issues associated with corn-soybean production systems. Our goal would be to reduce input per unit output by using crop rotation, cover crops, site-specific management, or various other improved nitrogen management practices. However, an even better approach would be to significantly increase crop yields while using better management with the same inputs. Nitrogen use and energy efficiency within corn-soybean systems are also influenced by other crop production practices, as evidenced by current ARS Renewable Energy Project Assessment or REAP team research showing that limited harvest of crop residues can make no-till production more successful in the Midwestern U.S. Corn-soybean energy issues, especially with regard to linkages between ethanol and energy prices, are closely linked with market signals. As energy prices increase, corn prices increase, but so do the costs of other inputs. Furthermore, as prices and input costs rise, the cost of incorrect nitrogen management increases, again emphasizing the importance of better management practices, including soil and plant analyses. Market linkages become even more complex if cellulosic ethanol is to be pursued, because it must account for increased nutrient removal, potential soil erosion or productivity effects, greenhouse gas release, and potential nitrate-nitrogen leaching effects. Market linkages also quickly moves many discussions into the complexities associated with economies of scale. Many argue that although current strategies have favored large farms, diversification could significantly increase energy use efficiencies. Some have suggested increasing landscape diversity by incorporating perennial woody and grass species into areas with lower corn-soybean productivity. This could positively affect ecosystem services, but how would it affect global market supplies for these commodities? Raising ecosystem service questions quickly moves the discussion of corn-soybean energy issues into boundary questions regarding environmental challenges, especially those associated with increasing weather variability and, of course, land conversion. The land conversion issue is much more of an international issue, but does affect energy discussions in the U.S. through debates regarding CRP and other land uses. The next step to further explore many factors affecting those energy issues is to conduct life cycle assessments. These were originally developed to quantify the full environmental effect of industrial systems. However, LCAs are now being used to determine greenhouse gas and soil organic carbon impacts of corn-soybean cropping systems, especially with regard to their use for bioenergy feedstock production. In other words, market and policy both affect the energy issues associated with corn-soybean and, for that matter, any other agricultural system. The complexity becomes even greater when uncertainties associated with variable weather patterns are included. Traditionally, market and policy influence corn-soybean energy issues primarily through production and distribution cost. This changed drastically in 2006 when agriculture was asked to begin supplying biofuel in addition to the traditional food, feed, and fiber outputs. This new demand on our agricultural production systems initiated many of the food versus fuel controversies, which reappeared in 2010 after a severe, prolonged, and historically unusual drought significantly reduced Russian wheat yields. As a result, the authors of this report stress that it is vitally important to have consistent biofuel and energy policies. This was also a conclusion reached by a recent Soil and Water Conservation Society sponsored workshop addressing sustainable feedstocks for advanced biofuels. In an attempt to stabilize market and demand, mandates are often used as a stimulus or short-term incentive. But unfortunately, these complicate market signals, creating uncertainty for both producers and consumers. So what is our strategy for addressing the multiple energy issues associated with corn-soybean systems? Our recommendation is to embrace the attributes of sustainability by developing a landscape vision for more sustainable and energy-efficient corn-soybean production. What is a landscape vision? Simply stated, it is recognizing nature's dynamics. It is also striving for balance. As shown in this diagram, which illustrates the competing demands between economics for feedstock supplies and the limiting factors needed to conserve soil and water and air resources. Why is diversity important? Because it addresses multiple ecosystem services, including energy production and use, nutrient cycling, filtering and buffering, wildlife habitat, productivity, and of course economic opportunities for humankind. How can a landscape vision be implemented into current agricultural systems, such as our corn-soybean model? First, we have to evaluate all current practices to fully understand how the current system is functioning, including its energy issues. Next, we have to know the options that will fit within the management capabilities of the landowner or operator. These should be reviewed and each considered for their opportunity to reduce energy use or to enhance energy use efficiency. Then, using the best spatial and temporal data available, consider redesigning the landscape to capitalize on as many ecosystem services as possible, including rural development. These factors will ultimately lead to more energy-efficient systems. With bioenergy as the new driver, plan for multiple technologies, multiple conversion platforms, and embrace multiple solutions. There does not have to be a one-size-fits-all mentality. Nature and natural systems do not operate in that manner. What barriers must be overcome to implement the landscape vision? Simply stated, we must stop addressing individual problems. The subtle externalities affecting energy issues and all other factors affecting sustainability must be considered. A landscape vision must address bioenergy, air quality, water quality, soil quality, wildlife, carbon sequestration, rural development, and other issues as an integrated system. This is not a new or unique concept in that my sister agency, the Natural Resources Conservation Service, has had this plan in their field office guidebook since 1993 in the form of their SWAPA plus E plus H model that they use to work with landowners and operators. In summary, economic, environmental, and market factors affecting energy issues for corn-soybean production systems are reviewed in this issue paper. Key conclusions are that we need to overcome barriers to energy conservation. Climate variation and land use issues must be better understood, and we must develop consistent system boundaries for effective greenhouse gas, life cycle analysis, and energy assessment. This issue paper has identified several research needs associated with energy issues affecting corn-soybean systems. We need to develop protocols to quantify those energy flow through complex systems. We also need to focus on quantifying no-till effects on carbon sequestration and greenhouse gases, striving for holistic land management using an integrated landscape management approach, and of course incorporating rural development and entrepreneurial opportunities using bioenergy as a catalyst, not as an endpoint. Finally, we need to strive for consistent federal, state, and local bioenergy policies that stimulate public and private investment. If you have any questions, please feel free to contact me at doug.carlin@ars.usda.gov, and be sure to download a free copy of the paper from the CAST website. Thank you for your attention.